Dear colleagues, let us start our BIM's Integrable System seminar. And today our speaker is Akihiro Hokkyo from University of Tokyo about integrability from a single conservation law for spin chains. So please, you are welcome.
Okay, thank you very much for the kind introduction. So I'm Akihiro Hokkyo from the University of Tokyo, and I'm happy to be invited to speak in this seminar series. And in this talk, I will present my recent work on a rigorous proof of a sufficient condition for quantum integrability. So let's start. So here's the outline of my presentation. So first, I'll give some background and explain the motivation, namely how one can verify integrability. Then I will introduce our main result, which shows that the single conservation law, known as the Reshetikhin condition, implies integrability. After that, I will discuss the possibility of a complete classification on integrability. Finally, I'll conclude with a short summary and an outlook for future research. And please feel free to interrupt me at any time if you have questions. So let me now begin with the first part of the talk. So as many of you know, quantum integrable models have long provided a unique window into the non-perturbative behavior of quantum many-body systems. Historically, they have played a central role in equilibrium statistical mechanics, most famously through Beatty's exact solution of one-dimensional quantum magnets. And in recent years, there has also been growing interest in their remarkable non-equilibrium dynamics, such as the absence of thermalization and the emergence of generalized hydrodynamics. There are no universally accepted definition of quantum integrability, but in this seminar, we take a standard definition for spin chains with local interactions. That is, a system is called integrable when it possesses an extensive number of local conserved quantities. For example, the well-known spin-1 half Heisenberg model is integrable in this sense. It has a three-body conserved quantity Q3, a four-body one Q4, and higher order conserved quantities as well. Having a large set of local conserved quantities is deeply connected to the distinctive properties of integrable systems I mentioned earlier. For example, the existence of infinitely many good quantum numbers is considered to yield the solvable structure of the model. Moreover, because these conserved quantities retain detailed information about the initial state, they also lead to remarkable non-equilibrium behavior, such as the lack of thermalization. So, as the presence of such unusual non-equilibrium dynamics already suggests, integrability is a non-generic and fine-tuned property. Recent rigorous results on non-integrability further support this expectation. Therefore, identifying integrable systems is a highly non-trivial task, since most physical systems are, in fact, non-integrable. A traditional approach to this problem is to try to solve the system in some way. The simplest examples are models that can be mapped to free fermionic systems, for instance, via the Jordan-Wigner transformation. For more complex interacting systems, an important and powerful method relies on the Yang-Baxter equation. So in the following, I'll briefly explain how integrability arises from this equation. The Yang-Baxter equation is this equation satisfied by a parameter-dependent matrix called the R matrix. Here, the subscripts indicate the spaces on which the matrix acts. Using this R matrix, we define a large matrix known as the transfer matrix. Then we can show that transfer matrices with different parameter values commute with each other. From this transfer matrix, one can construct the Hamiltonian and an infinite family of local conserved quantities. More concretely, the conserved charges Qn are defined through logarithmic derivatives of T lambda as this. Because the transfer matrices commute, all these Qn's commute as well. Furthermore, each Qn is known to be local, and in particular, Q2 corresponds to a Hamiltonian with nearest neighbor interactions. Therefore, the Qn's represent local conserved quantities of H, and we can conclude that the Hamiltonian H is integrable. We can also generate these conserved quantities in a simpler way using what's called the boost operator. The boost operator allows us to generate the conserved quantities successively. Formally, the boost operator can be defined in terms of the Hamiltonian density as shown here. From the Yang-Baxter equation, one can derive that the commutator between B and the transfer matrix T lambda is equal to the derivative of the latter with respect to lambda. In other words, this boost operator effectively raises the order of lambda, and therefore it generates Qn plus 1 from a given Qn. For example, we can write down the explicit form of the lowest nontrivial local conserved quantity Q3 as this. So far, we have seen how integrability can be derived starting from the Yang-Baxter equation. However, from the viewpoint of testing whether a given Hamiltonian is integrable, this approach is somewhat unsatisfactory. The reason is that the Yang-Baxter equation, or the corresponding R matrix, is not something that can be obtained directly from the Hamiltonian itself. As a necessary condition for a Hamiltonian to admit such an R matrix, there is a well-known criterion called the Reshetikhin condition. This condition states that the quantity generated from the Hamiltonian by the boost operator must be a conserved one. Written explicitly, it takes the form shown here, or this equation. And what's important is that this relation involves only the Hamiltonian density. Therefore, we can check the Reshetikhin condition algorithmically directly from the Hamiltonian. Since the Reshetikhin condition is a necessary condition for the Yang-Baxter integrability, it has long been used as a tool for classifying solutions to the Yang-Baxter equation. Beyond that, Grabowski and Mashu conjectured that the Reshetikhin condition might actually be a sufficient condition for integrability as well. Under this conjecture, the condition can be used as a heuristic test for integrability. Now, even though this conjecture was proposed more than 30 years ago, no counterexamples have ever been found in the studies based on the Reshetikhin condition. This strongly supports the idea that the conjecture could indeed be true. Nevertheless, it is quite natural to think that the infinitely many conserved quantities defining integrability should contain far more information than a single conservation law like the Reshetikhin condition. So the true status of the conjecture have remained uncertain. So to summarize the question, can a single conservation law, known as the Reshetikhin condition, lead to infinitely many conserved quantities, that is integrability? I give you a rigorous proof that the answer to this long-standing open problem is yes. Now, let me move on to the main result. I'll start by explaining the setup. we consider a quantum spin chain defined on an infinite lattice, where each side is labeled by an integer. The Hamiltonian density is taken to be a Hermitian operator consisting of a nearest neighbor interaction term and on-site term. From this, we define a translationally invariant Hamiltonian. And in analogy with Yang-Baxter integrable systems, we also introduce the boost operator in the same manner. Using the boost operator, we define the local quantities Qn recursively from the Hamiltonian. And as I mentioned earlier, Q3 can be written in this form. And now the main theorem states the following. If Q3 is a conserved quantity of Hamiltonian H, then for any n, the corresponding Qn is also a translationally invariant conserved quantity of H. For generic Hamiltonians, these operators Qn are non-zero and mutually distinct, and therefore the Hamiltonian H is integrable. So let me make a brief comment about the commutativity among the Qn's. So if the quantity generated by the boost operator commutes with the Hamiltonian, it is known that all the Qn's commute with each other. This follows directly from the Jacobi identity. For instance, when we take the commutator between Q3 and Q4, we can expand Q3 by the definition and use the Jacobi identity to reorder the commutators, and then observe that each term contains a commutator between H and some Qn, which vanishes by assumption. Therefore,
so I ask,
okay,
is it true that you have infinite number of sites because your summation is over the line?
yes. So this relation holds even in infinite system as long as the Hamiltonian is translationally invariant. So this is because, yeah, I will explain later, but this is just because computational relation is determined only on local finite number of sites, because in this case, Hamiltonian or other quantities is spatially consists of spatially local terms. Is it clear?
Assumption that you have infinite number of sites, is it true?
Yes. I assume that the number of sites is infinite.
Oh, okay, thank you.
Thank you very much. Okay, so yeah, so therefore, this theorem not only guarantees the existence of local conserved quantities, but also ensures that they are mutually commuting local conserved quantities. Okay, so yeah, although the theorem I presented in the previous slide was stated only for nearest neighbor interacting systems, the same result holds for systems with finite range interactions. So in this more general setting, the corresponding boost operator can be characterized as the operator satisfying this property. Yeah, I will use this property later. Yeah, but we can generalize the result to finite range interacting systems. And moreover, for certain integrable systems, most notably the Hubbard model, the boost operator does not exist. But instead, these models come equipped with a family of Hamiltonians depending on a continuous parameter, and they possess a generalized boost operator defined as a differential operator acting on this family. In such cases, A generalized version of the Reshetikhin condition is also known, and the theorem continues to hold in this generalized setting. And in addition, the results can be extended to models that may admit unconventional forms of boost operators. So let me now move on to the proof of the theorem, and first give you an outline of the argument. The proof proceeds by mathematical induction on n, and it is of course trivial for n equal 2. So first, regarding the translational invariance of Qn, this has already been established. And next, we show that applying the commutator with Hamiltonian twice to Qn gives 0. This follows quite easily from the Jacobi identity. And finally, using these two results, we show that the single commutator between the Hamiltonian and Qn itself vanishes. This part is somewhat technical, but formally straightforward. So let's now look at each step in detail. So to prove the translational invariance of Qn.
Can I have a question?
Yes, please.
We have this infinite Qn integral of motion, yes? What means that if you have structure coming from Young-Baxter, then is clear that they are transfer matrices commute and automatically commute on each other. So now when you're saying it means to independent something way you want to verify they are really commute or what? What you doing?
So first of all, I established this theorem without assuming any additional algebraic structure on the Hamiltonian, especially Yang-Baxter equation or something.
You have Hamiltonian, and you believe
yes.
that some extra conservation law, you're starting some to commute
yes.
and are they commute or not? Yes?
I assumed only that this Q3 is a conserved quantity of the Hamiltonian.
Yes.
Yes.
Only you know Q3?
Sorry?
Should come from the Young-Baxter. You know all Qn, you can write down them. You can verify, right? So now what you're doing something, I don't understand something, your logic. So you don't have Young-Baxter, then how are you writing this Qn integrals of motion? Only you you boost, you get so boosting the operators and verifying again this commute or not in that way, yes? Okay, so you don't use any Young-Baxter, just boost.
So
yes, okay. You want to
I haven't understand the meaning of your questions.
I understand. So question is following was. So you don't assume that Young-Baxter is satisfied. No?
Yes.
So you have
no, sorry. I didn't assume that the Yang-Baxter equation a priori, but assumes that this Q3, which is generated by the boost operator, is conserved. But it is not clear that the higher Qn is also conserved quantity of. This is somewhat, yeah, the conjecture. But I prove this is true for any Hamiltonian. So does this answer to your question?
Okay.
Okay. Yeah, thank you very much. So, okay, this space. Okay. Okay, so let's now look at each step in the proof in detail. So to prove the translational invariance of Qn, the key ingredient is this property satisfied by the boost operator. And here the calligraphic T denotes the translational operator. By using this property, we compute the translated version of Qn. The first, since translation is a unitary, we obtain the equality shown as 1. And next, by using the property of the boost operator, together with the induction hypothesis, namely the translational invariance of Qn minus 1, we obtain the equality 2. And finally, by using the induction hypothesis that Qn minus 1 is a conserved quantity, we find this coincides with Qn. So therefore, the translational invariance of Qn is established. So next step. So first, we rewrite the commutator between H and Qn. So by using Jacobi identity, we can reorder the commutators as this. And by applying the induction hypothesis that Qn minus 1 is a conserved quantity, we find that this expression becomes equivalent to the commutator between Qn minus 1 and Q3. And now, if we take one more commutator with the Hamiltonian, it immediately vanishes since both Q3 and Qn minus 1 commute with the Hamiltonian. So finally, let's move on to the last step. So let me start by recalling a simple but important fact about commutators of finite dimensional matrices. So that is, if the double commutator with the Hermitian matrix vanishes, then the single commutator must also vanish. So the proof of this fact is very straightforward, for example, by using the Hilbert-Schmidt inner product. So now, if we formally substitute x to the Hamiltonian and y to the Qn, we immediately obtain the desired conclusion that the commutator between H and Qn is 0. So however, we should keep in mind that this substitution is only formal, since both the Hamiltonian and Qn are operators in an infinite chain. So fortunately, because Qn is translationally invariant, as we have already shown, the commutator in the infinite system can be regarded as the commutators in sufficiently large finite systems with a periodic boundary condition. So therefore, this formal argument can be made rigorous, and the proof is complete. So before finishing, let me note that the translational invariance is indeed essential. So for instance, so let us apply the same formal argument with x to h. Then we have this naive expectation, but this is actually incorrect. Because if we take y as the boost operator, then this gives incorrect consequence. So this commutator between h and b is nothing but minus Q3. So this means if Q3 is conserved quantities, then Q3 is equal to 0. This is clearly false. So this property does not hold in general for infinite systems. But conversely, if the quantity is translationally invariant, then we interpret the commutator relations by using local densities, which live in finite dimensional space. And we can conclude in the correct way. So this is a mathematically precise statement of the this argument, but please refer to my paper for full discussion. So anyway, this completes the proof. Okay, so in the remaining part of my talk, I would like to combine our main result with existing result, in particular with the necessary conditions for integrability, to summarize what is currently known about the classification of integrable systems. Okay. So far, I've focused on a sufficient condition for integrability. But in recent years, there has also been remarkable progress on the necessary conditions and even on rigorous proofs of non-integrability. In 2019, Shiraishi proved that the spin 1/2 anisotropic XYZ chain in a magnetic field is non-integrable in the sense that there are no k local conserved quantities for any k greater than or equal to 3. So here, we clarify the terminology. An operator on the spin chain is said to be at most k local if it can be written as a sum of operators acting on at most k consecutive sites. For example, this figure illustrates the case of k equals 6. And furthermore, if an operator is at most k local, but not at most k minus 1 local, we simply call it k local. The Hamiltonian itself is, of course, a trivial to local conserved quantity. So therefore, Shiraishi's theorem states that there exist no local conserved quantities with a locality greater than that of the Hamiltonian. This is a precise meaning of non-integrability. Okay. So Shiraishi's approach has since been extended to many other systems. And furthermore, I developed a general framework that unifies and explains many of these results. In particular, we find the following. So consider a two local Hamiltonian with generic interactions. So here, the local Hilbert space dimension can be arbitrary as long as it is finite. Now suppose that for the quantity Q3 we have been discussing, any modification by adding another two local term Q prime 2 still leads to a commutator with a Hamiltonian that becomes 3 local. Then we can conclude that such a Hamiltonian is non-integrable. So I won't go into the technical details of what generic interactions precisely means here, but informally, it corresponds to the absence of on-site conserved quantities and the absence of any two local conserved quantities other than the Hamiltonian itself. So with these two assumptions in place, this theorem leads to a clear algorithm for proving non-integrability. So first, we verify the assumptions for the given Hamiltonian. And second, check the absence of any 3 local operator whose commutator with the Hamiltonian is at most 2 local. So despite dealing only with equations involving up to 3 local terms, so this procedure proves the absence of k local conserved quantities for any k. As a typical example, we consider the spin 1/2 anisotropic XYZ plus H chain again. So in fact, this model passes the first step. And we only have to consider the k equal to 3 case. So this is finally reduced to these 3 equations. And our theorem indicates that we don't have to consider general case, which was treated by employing these complex equations in the original method. Okay, so yeah, since we still have some time, so let me briefly explain the idea behind the proof of this theorem. So we introduce a helpful graphical language known as the string diagram formalism. So unlike the techniques we use, which is used in the original work, this notation has the advantage of being basis independent. And in this formalism, we represent the structure using lines and boxes. Here, lines correspond to operator spaces, and boxes represent linear maps between these spaces. So in our diagrams, the vertical direction corresponds to time, and the horizontal direction corresponds to space. As a special case of maps, an operator itself is drawn as a box without input wires. Here we also use 2 types of lines. Dashed lines represent the full on-site operator space, and solid lines represent the traceless subspace. 2 boxes can be composed by connecting their wires. And for example, the commutator of 2 operators sharing one site, I plus 1, is represented by the middle diagram shown here. The one advantage of this diagrammatic representation is that identities for commutators become visually obvious. For instance, this diagram can be interpreted in the 2 ways shown below, and these 2 interpretations use the same result. Okay. So first, let's illustrate the first assumption we imposed on the Hamiltonian using string diagrams. So we assume that this property, or precisely the existence of some maps mu and lambda for this commutator. So this serves as the left inverses to the commutator with Hamiltonian. And using these maps, we can peel off the commutator attached to the edge of an equation. So in this way. So now I explain the second assumption. So I assume this condition. So I will not explain the precise meaning of this condition, but this is informally equivalent that there is no candidate for the 2 local conserved quantities other than the Hamiltonian. And after flipping the next commutator, this condition can be expressed in the form shown here. So, and please remember this form. Okay. So the idea of the proof is to reduce inequality for a k local quantity to 1 for a k minus 1 local quantity. So as a warm-up, let us derive an equality for a 3 local quantity from 1 for a 4 local quantity. So first, we remove the commutator with the interaction that appears on the left-hand side of the left-hand side of the right-hand term. Yes. So using the resulting operator on the left, we define some 3 local operator. And substituting this expression back into the original equation, we obtain an equality of the following form. Then we remove the commutator with the interaction on the right-hand side of both equations, as shown on the previous slide, which is the desired 3 local equality. Okay, so the reduction from 3 to 2 proceeds in exactly the same way, but let me explain it explicitly. So we again peel off this commutator with the interaction, and using the operator that appears on the left, we define a 2 local operator, and substituting it back into the original equation is this equality. Then, just as in the previous slide, we remove the commutator with the interaction on the right side of both equations, and this gives the 2 local equality. And please note that this is nothing but one appears in the second assumption. Okay, so summarizing what we have done so far. So starting from a 4 local quantity, we have reduced it to a certain 2 local quantity. Here, the initial equation is in fact equivalent to the statement that the commutator between the 4 local quantity and the Hamiltonian is at most 4 local. And using the second assumption, this 2 local quantity can be completely solved, and the original 4 local conserved 4 local quantity must take the following form. And this is very similar to that generated by the boost operator. Okay, so the overall strategy remains the same structure. So we successfully reduce the problem to smaller values of k. And here the induction hypothesis is weaker than the existence of conserved quantity. We only assume that the operator commutes with the Hamiltonian up to a k-1 local term. And under this assumption, we eventually arrive at the contradiction with the stated assumptions, which leads us to conclude non-integrability. Okay. The second theorem I presented earlier is closely related to another conjecture by Grabowski and Masur concerning integrability. The assumptions in that theorem are stronger than merely requiring the absence of 3 local conserved quantities, as this. So based on studies of non-integrability, it has been conjectured that this assumption alone already implies non-integrability. And this conjecture can be reformulated in an almost equivalent way. So namely, any integrable system must possesses a 3 local conserved quantity. This is another conjecture proposed by Grabowski and Masur. And while our second theorem in this talk has been sufficient, while the first theorem of this talk has been sufficient conditions for integrability, this conjecture represents a necessary condition for integrability. So our second theorem, although in a weaker form, provides a rigorous foundation for this type of statement. Okay, so let us now combine the sufficient and necessary conditions for integrability that we have obtained so far. So to the best of our knowledge, Hamiltonians fall into one of 2 distinct categories. So there is an integrable, meaning that they possess infinitely many local conserved quantities, or non-integrable, meaning that they have no local conserved quantities beyond those with the same locality as the Hamiltonian itself. Can we fully explain the underlying structure behind this dichotomy? So with the sufficient conditions for integrability and non-integrability that I presented today, we can now determine, in the regimes covered by their assumptions, whether a given system falls into either category, as this. So however, there still remains a third case where neither condition applies. So this does not yet constitute a complete classification. So let me conclude this seminar with an outlook and summary. Okay, so first I discussed the outlook. So in the previous slide, I talked about the possible way to establish a sharp dichotomy between integrable and non-integrable systems. So applying this framework to specific class of Hamiltonians is the most straightforward and immediate application of our result. So fortunately, a very recent work by Shiraishi and Yamaguchi has successfully proved such a sharp dichotomy for spin chains with SU2 symmetric nearest neighbor interactions using this approach. And extending such a result to more general systems will be an important direction for future readers. Or we may find some partially integrable model, which means that the system which is not integrable and not non-integrable in our sense. So this is first outlook. And another key open question is whether the Reshetikhin condition implies the Yang-Baxter equation. So this relationship is summarized schematically in this figure. So in this work, so we prove that the Reshetikhin condition implies integrability for this direction. So this means that all the information about local conserved quantities contained in the Yang-Baxter equation is already encoded in the Reshetikhin condition. Whether this implication can be extended to the full algebraic structure of the Yang-Baxter equation, or whether integrability is in fact strictly weaker than the Yang-Baxter framework, remains an important and fascinating problem for understanding the mathematical structure of quantum integrability. So now we move on to the summary of this presentation. So I showed that the Reshetikhin condition, which was long conjectured to be a sufficient condition for quantum integrability, indeed guarantees integrability. And this result establishes that a single conservation law can imply the existence of infinitely many local conserved quantities, providing a foundation of a criterion for identifying integrable systems. And combining with the recent result on non-integrability, this provides a clear criterion for identifying whether a system is integrable or not. And although a third unresolved case still remains, our findings point toward a possible dichotomy theorem that could give a complete classification of quantum integrable systems. Okay, this is the end of my talk. Thank you very much for your attention.
Okay, thank you very much for your talk. Questions?
I have two questions. First, how do you get new integrable system in this way?
The answer is no. So actually, this previous result by these groups indeed found new integrable systems by using Reshetikhin condition.
Okay. Good. Second question. So you see, you think that's something one can prove that the using Reshetikhin, this condition, yeah, boost this you wrote this, so this condition. Is it mean that this is something, some deep algebraic conditions? Can you? It means that is it possible in some sense equivalent to the Young-Baxter? Yes, as you're saying.
So
it's algebraically deep condition. This is how we can understand more something simpler. Is it possible to clarify more?
Okay, so yeah, first of all, so almost about such a thing is almost open problem, but so I conjectured that the Reshetikhin condition indeed implies the Yang-Baxter equation. So, but yeah, I'm not sure what is mathematical and physical mechanism of this implication. Yeah, sometimes, yes.
Clarify
please.
Completely. That's really very interesting.
Yeah. Yeah, sometimes people say that the Yang-Baxter equation makes three-body problems to two-body problems. Then many body problems also leads to two-body problems, which we can solve. And I guess similar mechanism lies in the local conserved quantities. Two local conserved quantity is trivial, which is Hamiltonian, but the 3-1 is simplest non-trivial one. And if such a quantity exists, then we can make higher one by boosting it. So it should be related, but I'm not sure.
Sorry, can I ask you something?
Yes, please.
Okay, so I have a few questions. Simplest probably with no answer. So could you clarify, did you find any examples of integrable spin chains that doesn't have arithmetic structure?
Sorry, that have what?
Any integrable model, new or old, without Yang-Baxter symmetry?
I didn't find such a model.
Okay, that's okay. And then another question. So what happens if it's specific integrability when you have finite number of local Hamiltonians and the rest would be non-local? From your point of view, it's called non-integrable system, yes?
Sorry, your question is about?
What if in our Hamiltonian system, we have some of them local, like 10 finite number, and the rest, infinity number, would be non-local Hamiltonians. From your classification, it's called non-integrable. Yes or not?
Sorry, I couldn't catch your question. So about the definition of non-integrability. So I say the system is integrable if the system possesses infinitely many local conserved quantities, and non-integrable if they have no local conserved quantities beyond those with the same locality as the Hamiltonian itself. So if the Hamiltonian consists with two local one, then the non-integrable means there is no 3, 4, 5 blah, blah, local conserved quantities.
Sorry, but there is examples of non-integrable system without a third, but with only even integrable of motions, like 2, 4, 6, and so on. But there is no Q3.
So do you know such an example? So I don't know such an example.
Yes, I know. Probably you also know it can be reformulated in other terms. If you think about inhomogeneous spin chains, with inhomogeneity that switch one-to-one, I mean, plus something minus something, like with this even symmetry.
So sorry. So, yeah, I didn't. So yeah, can I contact with you later? So
yeah, I will try to send you something.
Yeah. Thank you very much. So yeah, basically, this is counterexample of this old conjecture, I think.
You have very special definition of integrable because it's not common integrability. You have your own. So I'm not sure that it's a counterexample, but it's definitely integrable. But I'm not sure what you mean exactly when you say integrable.
So yeah. Okay. So yeah, but anyway, so I didn't know such an example. So
okay, and probably the last question: do you know any possible generalization of boost method to the non-local integrable system like Haldane-Shastry or Innocential spin chain?
Yeah, I learned from some people, but yeah, I'm not sure. Yeah, I know there is some method, but yeah, rigorously speaking, my proof is based on locality, as I mentioned in this slide or some slides. So yeah, mathematically speaking, I don't know.
More questions?